Welcome to the solution video for CNCM Online Round 2, Problem 4. My name is Harry Chen. So the problem goes as follows. On a chessboard with 6 rows and 9 columns, shown below, the slow rook is placed in the bottom left corner, so over here, and the blind king is placed on the top left corner, over here. Then 8 sleeping pawns are placed such that no 2 sleeping pawns are in the same column. No sleeping pawn shares a row with the slow rook or blind king, and no sleeping pawn is in the rightmost column. So that means we have to place one here, 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 and here. The slow rook can move vertically or horizontally one tile at a time. The slow rook cannot move into any tile containing a sleeping pawn, and the slow rook takes the shortest path to reach the blind king. How many ways are there to place the sleeping pawns such that the slow rook moves exactly 15 tiles to get to the space containing the blind king? And so basically what this means is that the slow rook is going to move something like this and something like that, and then I don't know, maybe there's an opening in this column, so it decides to go up, and then I don't know, maybe there's like a pawn here and like a pawn there, and so it decides to move left, and then it moves up, and then it moves back to the blind king. So that would be an example of something that would work, because it would move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, it moves 15 tiles. Yeah. And so the important thing to realize here is that, so you see how this, the rook went through the little gap here? Well, that can only happen if the 2 pawns are spaced at least 2 tiles away. If they're spaced any closer, so let's say there's a pawn here, then the rook cannot pass through this area here. And it can't move like through this either. So it's stuck. That'll be important for later, so keep that in mind. But before we use that information, we'll use this. We have to prove that the slow rook will never move down. That is to say that it'll only move either right, up, or left. And so to prove this, we just kind of play around with it a little bit. So let's just say the slow rook moved all the way up here and then moves up. We want to prove that if it's going to get to the blind king, then it's not going to move down, or that it would be inoptimal for it to move down. So that's actually not that hard to prove. We just have to play around a little bit. So so let's say the rook goes up here, it moves left. Let's just say, well, if it moves left, then we could have just went up here. So it's not going to move left. If it moves right, then I mean, I guess it could go up or it could go right, but it's this exact same thing as just going like that. And so it basically just moves the problem one space to the right. So we don't have to worry about that. So let's just say it continues forward. If it continues forward, let's say it goes left, right? If it goes back down, it wastes a move basically, or wastes 2 moves. So it moves left. So if there's a pawn here, then it'll just go straight to the blind king. So it won't move down in that case. If there's not a pawn there, so let's say there's a pawn here or a pawn on the 4th space, then there can't be a pawn here, so that means the blind king could have just went like this. And so we just moved the problem one space to the left, and so it's not really an issue. And so we can just pretend like it doesn't go left here. So the same argument as when we went off to the right over here. And then we can use similar reasoning on the right over here to just kind of reason it out that it's just moving the problem one space to the right. So it doesn't really matter there. So we're going to assume again that it moves one space up. It's not going to move down, of course. If it moves left, we already know that the pawn has to be here, or else it's just going to move directly into the blind king. If it moves it up here, well, we could have just went like this, right? And so, yeah, so just move the problem one space to the left, essentially. Or sorry, it could have went like this. Yeah, sorry, it could have went like directly up like that. Yeah, so we can just safely assume that it's not going to move left there. If it moves right, similar reasoning, could have just went like this, or yeah. And so finally, let's just assume it goes up again. If it goes up again, well, now it can just reach the blind king. And so in none of those cases did it actually move down, because there was no reason for it to move down ever. And if we move left or right, well, it just moved the problem one space to the left, or one space to the right, and so we can just use almost the exact same reasoning we just did to deduct that it won't move down in that case either. It's a pretty nice solution. But anyway, a corollary of this is that we actually get to know exactly how many times it's going to move left, right, and up. It's of course going to have to move up exactly 5 times because it's never going to move down, and this is the blind king's always 5 above it. It's going to move right a total of 5 times, and it's going to move left a total of 5 times because it has to move an equal amount of spaces left as right, and so yeah. Okay, now we actually apply this. So using that corollary, we can kind of see that the only way for the slow rook to actually get to the blind king in exactly 15 spaces, if we have something like a wall here made out of straight pawns that are adjacent to each other, and then just some sort of gap on this 6th row here, because in this case it can move, it'll move like this, and yeah. It moves 5 spaces up, 1, 2, 3, 4, 5 spaces to the right, and then 5 spaces to the left. We can kind of reverse this as well. Maybe it doesn't have to go, maybe it isn't like that, maybe it's like that, in which case the slow rook will move like this. And so that's basically what a possible configuration would look like. 5 adjacent pawns in the first 5 rows, and then in between these 2 rows, the 5th and 6th rows, they are at least 2 apart. So how do we actually compute this then? So we compute this as we're going to use recursion. So basically we have this table down here. This table is going to be basically how many ways are there to arrange the pawns such that, so for instance in this row, the number we write down here is the number of ways to arrange the pawns such that the pawn in the nth row here, sorry, in the nth column here, well, I guess such that how can we place the pawns up to the nth column? So in this case would be up to the first column, up to the second column, such that all the pawns are adjacent, and it ends in a pawn in this row. So yeah, so for instance, the number in this would be the number of ways to have the pawns ordered such that, I don't know, something like this happens, where they're adjacent up to the second column, and it ends on the first row. Yeah, so obviously these first ones all in column 1 will all be 1, because I mean if we for each of these columns you just got to place it in the row. So for this number here, we just have to place a pawn here, and then we're done. That's the only possible way to do it. But it gets a little bit more complex for the second column here. So basically, we're gonna try to find a recursion for this. So it only actually, so the number that's in this space here only really depends on the numbers in this column, in the first column, because we know that has to be adjacent to this one. And so we can say that if we let, you know, here we'll let a1, n, so this is the row, and then this is the column. handwriting's bad. So yeah, a underscore 1 comma n is going to be equal to a 1 comma n minus 1 plus a underscore 2 comma n minus 1. So what does this mean? That means the number that we put here is going to be equal to this number here plus this number here. Why? It's because for either of these two, so if the previous configuration ends on the first row, then we can just put upon. So okay, so let's just say we have, if we have a configuration list to get the 1 comma 2, so this space here, we just have to put upon here, and then that's a way to do it. Alternatively, we could have some configuration such that in the previous column it ends in the row 2, because we can also put a upon here because it's adjacent to it. Still, it's one away, but it's adjacent to it. And so if this works for all possible columns. So even for column 3 here, if we have this, so it ends in the first row, we can just put upon here, and they're still all adjacent. Alternatively, if we have upon here, well, they're still all adjacent and they still end here, and the previous one in column 2 ends in row 2. So that's basically how we derive this. And then likewise, if we want to count how many possible ways there are to do it in the second row, basically one of the inner rows, then we instead of summing a underscore 1 comma n minus 1 and a underscore 2 comma n minus 1, we would sum up a 2 comma n is equal to a 1 comma n minus 1 plus a underscore 2 comma n minus 1 plus a underscore 3 comma n minus 1 for similar reasons. We can put upon here that's adjacent to either the first, second, or third row, and so that's where we got all these terms from. If this is confusing, you can watch our recursion lecture that explains it a little bit better. But yeah, and so basically we used these two formulas to extrapolate the rest of the data. Oh yeah, by the way, for row 3 and row 4, by symmetry, the equation for row 3 is the same as the equation for row 2, and the equation for row 4 is the same as the equation for row 1. And so we can just compute this out. So over here, this is going to be the sum of 1 plus 1, so 2. This is going to be the sum of 1 plus 1 plus 1, so 3, 3, 2. This here is the sum of 2 plus 3, so 5. The sum of 2 plus 3, which is 8. 8, 5, that's not an 8, there we go. And yeah, we can keep continuing this process, 13, 21, 21, 13, 34, 55, 55, 34. So that's actually kind of cool because it's the Fibonacci numbers. It's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. And it kind of makes sense. You can prove it by induction. So this 5 is 2 plus 3. So this 13 is 5 plus 8. 34 is 13 plus 21. And so, I mean, if you add up any two consecutive Fibonacci numbers, you get the next Fibonacci number. So that's why the first row is all Fibonacci numbers. And the second row is Fibonacci numbers is because if we have something like 21, 5 plus 8 plus 8, that's equal to 13 plus 8. And we know that 13 and 8 are consecutive Fibonacci numbers, which gets us the next one, which is 21. So it's pretty cool. If you kept going, you would get more Fibonacci numbers, but we can just stop right here. Because remember, we only need, if you remember, we only actually need the first 5 to be consecutive. So we can just stop here at this column. But now we're not actually done though. So we have the first 5. These are the number of ways to organize the first 5 such that they are consecutive. but we still need to determine all the different, count how many placements there are for the sixth row here, sixth column here. Yeah. So if it's in the second or third row, we know there's only one way to place it, and that's on the very edge here, on the opposite end. So there's only one way to do it for 55 and 55. Alternatively, if it's on the outside, if it ends on row 1 or row 4, there are two ways. We can either put it here or we can put it here in the third and fourth row. So there are two ways. So compute this. We have, by symmetry, we can multiply everything by 2. So 2 times 2 times 34 plus 55. And then we got to multiply this all by 16 at the end, or 4 squared, because we can pretty much order these two columns however we like. Yeah, and so there's 4 ways to order it here and 4 ways to order it here, so that's 16 extra ways. And so we calculate this equal to 3936. And we are done. Thank you for watching. And the more videos will be released.